Imagine a universe not solitary and finite, but one in a ceaseless waltz of cosmic cycles, eternally dying and being reborn. Welcome to the conformal cyclic cosmology, a brainchild of Sir Roger Penrose, challenging the conventional Big Bang narrative. This model introduces the concept of conformal invariance, making our universe's birth and eventual infinite future almost indistinguishable when viewed through the lens of scaleless space-time. In this grand cosmic opera, the protagonists are the black holes, their evaporation through Hawking radiation serving as the universe's entropy reset button, providing a clean slate for the next cycle. The tantalizing clues of this cyclical existence: mysterious Hawking points, imprints in the cosmic microwave background radiation, potentially echoes of a universe past. Step into the fascinating dance of universes, and let's explore the profound implications of the conformal cyclic cosmology model. What is conceptual basis of conformal cyclic cosmology? Dare to imagine, if you will, a universe that lives, dies, and then rebirths itself in a majestic cosmic cycle that stretches to the boundaries of eternity. This isn't a science fiction fantasy, but a radical cosmological theory known as conformal cyclic cosmology, introduced by Sir Roger Penrose. In traditional cosmology, we understand the universe as originating from the Big Bang, a singularity from which all space, time, and matter sprung into existence some 13.8 billion years ago. However, the conformal cyclic cosmology theory turns this notion on its head. It proposes not just one Big Bang, but an infinite succession of them. Each Big Bang marks the dawn of a new eon, a fresh universe that replaces the old, much like a phoenix rising from the ashes of its predecessor. The conformal cyclic cosmology model hinges on the property of conformal invariance, a strange feature of the universe where shapes can be stretched or squashed without affecting their fundamental nature. At the universe's birth and death, the Big Bang and the infinite future, the theory suggests the cosmos becomes conformally invariant. In this peculiar state, notions of space and time as we know them cease to hold sway. The universe's expansive future becomes indistinguishable from a new universe's infinitesimal beginning, thus enabling the transition from the old universe to the new. The lifeblood of this cyclic universe is entropy. Black holes, those insatiable cosmic beasts, swallow up information, a manifestation of entropy, until they finally evaporate through the elusive process of Hawking radiation. This, Penrose suggests, is the universe's natural way of resetting its entropy, preparing itself for a fresh cycle of birth, life, and death. Thus, through the lens of conformal cyclic cosmology, the universe becomes an eternal symphony, endlessly cycling through movements of expansion and renewal. This theory beckons us to revise our understanding of the cosmos's origin and destiny. Instead of seeing it as a linear journey from a singular beginning towards an uncertain end, we are encouraged to imagine a grand cosmic waltz, an infinite dance of universes, each one giving birth to the next in a majestic and perpetual cycle. So let your mind wander into the vastness of infinity, for within it might lie the secret cycles of the cosmos. How is the concept of conformal invariance applied at the beginning and end of each cycle in the conformal cyclic cosmology model? How does this affect our understanding of space and time? Picture a universe, a beautifully intricate fabric of space and time, stretched to the furthest extremes of existence. Now imagine, if you can, that fabric being reshaped, stretched, squashed, and yet maintaining its core essence. This is the magic of conformal invariance, a vital concept that lies at the heart of Roger Penrose's conformal cyclic cosmology. The notion of conformal invariance is deceptively simple. Structures, patterns, and laws of physics remain unaltered under changes of scale. This means that no matter how you stretch or squeeze space and time, the fundamental nature of the universe remains the same. The equations of physics retain their form. They are indifferent to these transformations. However, in the grand ballet of cosmic existence as proposed by conformal cyclic cosmology, this property of conformal invariance takes center stage during two pivotal moments: the birth and death of the universe, known as the Big Bang, and the infinite future, respectively. In the incandescent furnace of the Big Bang, space-time is incredibly dense and compact. As we journey through the eons to the universe's infinite future, it becomes unimaginably dilute and vast. Now here's where the magic of conformal invariance comes in. If we strip away the scale of space-time, meaning if we remove our familiar notions of size and duration, these two extreme states of the universe start to look eerily similar. That infinitesimal dot of the Big Bang and the infinite expanse of the future universe become indistinguishable when viewed through the lens of conformal geometry. This is the key that allows the universe to cycle endlessly according to conformal cyclic cosmology. Each universe's infinite future is seamlessly connected to the next universe's Big Bang, like adjacent frames in an unending cosmic movie. In this majestic cosmic waltz, the dying echoes of one universe become the birth cries of the next. So what does this mean for our understanding of space and time? It invites us to see them not as fixed, immutable backdrops against which the universe unfolds, but as dynamic entities that stretch, dilate, and transform across the endless cycles of cosmic existence. The conformal cyclic cosmology theory nudges us to think of the universe not as a solitary creation, but as an eternal symphony of recurring space-time patterns, forever shifting and rebirthing in a dance choreographed by the sublime rules of conformal invariance. How does the notion of time and scale in conformal cyclic cosmology become blurred due to conformal transformations? And why does Penrose propose that the vast future universe becomes indistinguishable from another universe's Big Bang? In conformal cyclic cosmology, Penrose utilizes the concept of conformal transformations, a mathematical tool used to examine the structure of space-time in a unique way. These transformations preserve the shape of objects, but can stretch or shrink their sizes. In this sense, they allow us to zoom in or zoom out, without distorting the basic geometry of space-time. Applying these transformations to the universe's timeline, Penrose proposes a fascinating idea. When we zoom out far enough, the vast, infinitely expanded future of one universe becomes indistinguishable from the highly compressed, dense state of the next universe's Big Bang. This is like viewing the universe through a cosmic fisheye lens, where the distant future and the far past become blurred together. So how does this idea affect our understanding of time and scale? Typically, we view time as a linear progression, moving from the past through the present and into the future. Similarly, we often view the universe's scale in terms of its ongoing expansion, growing larger and more spread out over time. However, in conformal cyclic cosmology, these traditional notions are turned on their heads. Time, in the context of conformal cyclic cosmology, becomes cyclic rather than linear. Each universe's timeline is like a circle, starting with a Big Bang, progressing to an infinitely distant future, then looping back around to the next Big Bang. As for the universe's scale, it no longer progresses in a straight line from small to large. Instead, it oscillates from extremely small at each Big Bang to extremely large at each infinite future, then back to small again. It's worth noting that this radical reinterpretation of time and scale is one of the most philosophically challenging aspects of conformal cyclic cosmology. It pushes us to reconsider our most basic assumptions about the universe and our place within it. However, it's also part of what makes the conformal cyclic cosmology model so intriguing, offering a fascinating new perspective on the eternal dance of cosmic birth, death, and rebirth. What does it mean for there to be an infinite succession of universes? What implications does this have for our understanding of the universe? Within the heart of Sir Roger Penrose's conformal cyclic cosmology lies a notion that is both utterly fantastical and profoundly mesmerizing: the concept of an infinite succession of universes. This is not just a solitary universe, born from a singular Big Bang, existing for a cosmic lifetime before fading into an uncertain future. Instead, the conformal cyclic cosmology portrays a grand cosmic opera that has no beginning and no end, a series of universes each rising from the ashes of its predecessor in an eternal cycle of birth, death, and rebirth. This cyclical view of the universe invites us to reassess our most fundamental assumptions about the nature of existence itself. If our universe is but one link in an infinite chain of cosmic epochs, then what does this mean for our understanding of time, space, matter, and even the laws of physics themselves? The concept of time, for example, morphs into something far more fluid and complex. Instead of seeing time as a straight line stretching from the Big Bang to the far future, we must consider it as a vast, endless cycle, forever looping back onto itself. Each cycle, or eon as Penrose describes it, gives rise to a new universe, each with its own unique progression of time. Then there is space, which in this model isn't a static stage upon which the cosmic drama unfolds, but a dynamic entity that is born, grows, and finally fades, only to be reborn anew. It's a view that imbues space with a life cycle of its own, akin to the natural cycles we see on Earth. The infinite cyclic nature of the universe also casts a fresh light on the mysteries of matter, energy, and the fundamental laws of physics. Could the laws we regard as inviolable constants be subject to change over vast cosmic cycles? Might the matter and energy that comprise our universe have been recycled from previous universes, and will they too become the building blocks for future universes? At its core, the notion of an infinite succession of universes transforms our perspective of existence from a solitary, one-time event to an eternal recurring process. It's a concept that not only broadens our cosmic horizons, but also invites us to ponder profound questions about the very nature of reality. Whether or not the conformal cyclic cosmology model withstands the test of scientific scrutiny, it certainly propels our imagination towards the infinite possibilities of the cosmos. How does the conformal cyclic cosmology model address the issue of entropy? If the universe cycles endlessly, how is the increasing entropy resolved? And how does the universe reset its entropy to a low level at the beginning of each cycle? If you've ever watched a sandcastle being relentlessly pounded by the waves until its form is lost to the sea, you've seen entropy in action. It's a fundamental principle of the universe, a law that dictates the inevitable progression towards disorder. Yet this poses a peculiar conundrum in the framework of conformal cyclic cosmology. In an eternally recurring universe, how does one reconcile with entropy, which should, by all accounts, be forever on the rise? The answer, according to Sir Roger Penrose, lies in the vast cosmic monsters we know as black holes. In the cosmic saga of conformal cyclic cosmology, black holes play a pivotal role. As these gargantuan entities feast on surrounding matter, they become the ultimate hoarders of the universe, swallowing not just matter and energy, but also the associated entropy. However, these astronomical beasts don't live forever. Given enough time and almost unimaginable span in human terms, they eventually disintegrate through a phenomenon known as Hawking radiation. Here's where the narrative takes an intriguing twist. As a black hole evaporates, it essentially erases the information and entropy it had previously consumed. This natural cosmic process, over an incredibly long time scale, is effectively a reset button. By the time the universe has expanded into the infinite future, and all black holes have evaporated, the entropy of the universe is restored to a remarkably low state. Yet the process isn't as simple as flipping a switch. The dying breaths of the black holes leave a trace on the universe, imprints known as Hawking points, that carry with them a whisper of the universe's past. In the grand cycle of conformal cyclic cosmology, these points serve as the seeds of the forthcoming eon, the newborn universe. Thus, conformal cyclic cosmology posits a universe in perfect balance, where the inexorable rise in entropy is counteracted by the cyclical nature of cosmic life and death. Each successive universe emerges from the ashes of its predecessor, reset to a low entropy state, ready to embark on its own cosmic journey, while carrying forward echoes from its ancestral past. This perpetual dance between entropy, black holes, and the universe's birth and death challenges our conventional understanding of cosmic evolution and presents a tantalizing view of an eternal cyclic cosmos. Are Hawking points truly detectable? If so, how can we definitively identify these as signs of a previous universe? In the cosmic story woven by conformal cyclic cosmology, there are few elements as intriguing as the concept of Hawking points. Named after physicist Stephen Hawking, who proposed the phenomenon of black hole evaporation, these points are theorized to be the last dying whispers of evaporating black holes from a previous eon or cosmic cycle. The story goes like this. In the distant future of an eon, black holes have swallowed massive amounts of matter and entropy. However, given a sufficiently vast timescale, these black holes eventually disintegrate through Hawking radiation, a quantum process that slowly whittles away their mass. According to Roger Penrose, the key architect of conformal cyclic cosmology, the end of this evaporation process sends a final burst of radiation into the subsequent eon. This radiation, carrying a slightly higher temperature, is what we term as Hawking points. However, are these vestiges of a past universe truly detectable? According to conformal cyclic cosmology, yes. These Hawking points should appear in the cosmic microwave background, CMB, the omnipresent radiation echo of our own universe's birth. As regions of slightly elevated temperature, these points should be detectable as circular anomalies in the CMB. But here's the crux. How can we be certain that these Hawking points are indeed relics from a previous eon, and not just random noise or artifacts from our own universe? This is a contentious issue. Some scientists argue that these temperature fluctuations could be caused by a myriad of other phenomena within our universe, or simply be statistical anomalies in the CMB data. To decisively identify these Hawking points as signs of a previous universe, we would need a level of statistical confidence that rules out other possibilities. This requires rigorous analysis of vast amounts of CMB data and developing a deep understanding of all the processes that could potentially affect the CMB. We would also need to corroborate this data with other independent lines of evidence that support the conformal cyclic cosmology model. Such definitive evidence has not yet been established, and the existence of Hawking points remains a topic of vigorous debate. But who knows what future observations and developments in theoretical physics might reveal? Perhaps one day we will be able to gaze into the night sky and find unmistakable signs of a universe that came before our own, etched in the subtle glow of Hawking points. What empirical evidence supports the conformal cyclic cosmology model? How can the claims made by this model be tested and verified? The audacious propositions of conformal cyclic cosmology, while deeply fascinating, also pose a significant challenge. For this theory to move beyond the realm of mathematical beauty into scientific acceptance, it must stand up to empirical scrutiny. So what empirical evidence might support this model, and how can we put conformal cyclic cosmology to the test? The primary empirical prediction of conformal cyclic cosmology relates to the cosmic microwave background, CMB, the pervasive afterglow of our universe's birth. Conformal cyclic cosmology hypothesizes that signs of the previous universe should be detectable in the CMB, specifically as Hawking points, regions of slightly elevated temperature due to the radiation burst from evaporating black holes in the previous eon. Roger Penrose and his team have indeed claimed the detection of such anomalies in the CMB, suggesting these could be empirical evidence for conformal cyclic cosmology. However, these findings have been met with substantial skepticism within the scientific community. Critics argue that the anomalies might be statistical noise, or perhaps signatures of phenomena within our own universe rather than echoes from a previous cosmic cycle. This brings us to the crux of the matter. How can the conformal cyclic cosmology model be tested and verified more conclusively? A crucial step would be a detailed, exhaustive analysis of CMB data. This would require not just the identification of potential Hawking points, but also ruling out other explanations for these anomalies. We would need to determine with high confidence that these points are not mere statistical flukes or artifacts of processes within our own universe. Furthermore, conformal cyclic cosmology might make other unique, testable predictions. For instance, it might suggest specific patterns in the large-scale structure of the universe, or unique signatures in gravitational waves. Finally, any empirical support for conformal cyclic cosmology would need to fit coherently with the broader body of cosmological data and understanding. The theory would need to not only explain the observed anomalies, but also align with the wealth of existing observations about the universe's history, structure, and evolution. This is a high bar to clear, but it is the nature of empirical science to continuously question, test, and refine our understanding of the cosmos. How does the conformal cyclic cosmology model compare to other cosmological models, such as the Big Bang model or other cyclic universe models? What advantages does it offer over these models, and what challenges does it face? Conformal cyclic cosmology is a captivating challenger on the cosmological stage, offering a radically different take on the universe's origin and fate compared to traditional cosmological models. In this dramatic reimagining, the universe exists not as a one-off firework display that began with the Big Bang, but as an eternally repeating cycle of cosmic rebirths. But how does conformal cyclic cosmology fare when compared with other cosmological models? Let's start with the reigning champion, the standard Big Bang model. Backed by robust empirical evidence such as the CMB and the observed large-scale structure of the universe, this model posits a single origin for our universe approximately 13.8 billion years ago. Conformal cyclic cosmology, while not discarding the Big Bang as an event, reinterprets it as a cyclical process rather than a singular occurrence. An advantage of conformal cyclic cosmology here is its attempt to resolve what happens before the Big Bang and after the universe's heat death. areas where the standard model falls silent. However, a significant challenge is that conformal cyclic cosmology lacks the extensive empirical backing that the Big Bang model enjoys. The suggested Hawking points in the CMB as evidence for conformal cyclic cosmology are highly contested. Comparing conformal cyclic cosmology with other cyclic models, like the ekpyrotic cyclic model proposed by Steinhardt and Turok, reveals similarities but also key differences. Both advocate an endless cycle of universes, providing a refreshing take on the universe's destiny. However, the nature of these cycles and the mechanisms driving them differ substantially. The ekpyrotic model involves higher dimensional brane collisions to trigger each cycle, while conformal cyclic cosmology hinges on conformal transformations and black hole evaporation. A potential advantage of conformal cyclic cosmology is its minimal appeal to higher dimensions or string theory, which are yet unproven. But a common challenge both cyclic models face is providing concrete, testable predictions that set them apart from the standard model and each other. Lastly, it's important to acknowledge the philosophical appeal of conformal cyclic cosmology, addressing existential questions about the universe's origin and fate in a unique, thought-provoking way. However, it must also surmount significant hurdles, including providing robust empirical evidence and resolving potential issues like the entropy problem. The journey towards acceptance in the scientific community for any new cosmological model is an arduous one, and conformal cyclic cosmology is no exception. It will be fascinating to see how this bold theory evolves and is tested in the coming years.